Hello. Okay, should be good now.
Hello.
Yeah, I think it's.
Yeah, this gives me some time to breathe. And then this is the El Nino condition. So during El Nino time, the easterlies over the equatorial Pacific weaken. So and there is mainly westerly anomalies which push the warm water toward east and make East Pacific anomalously warm, and this flatten the thermocline over the equatorial Pacific, and more convection is happen over the eastern Pacific region. And La Nina condition is a extreme condition of the neutral state. So you can see there is a more thermocline slope and more convection over the West Pacific because of the stronger westerlies. Now there are many mechanisms which try to explain the ENSO. So mainly the most common is the tropical Pacific sea couple processes like delayed oscillator, recharge discharge, and westerly wind burst. But I will not talk about this. My focus in the extratropical Pacific impact on the ENSO generation. So this is more and more prominent that the extratropical Pacific has a strong impact on the tropical Pacific, and these are the few mechanisms which is now vigorously used to explain this. So North Pacific meridional mode and seasonal footprinting, which is mainly associated with heat flux driven part of the North Pacific oscillation, and trade wind charging mechanism, which is the ocean dynamics driven part of the extratropical forcing. So our main focus is in this trade wind charging mechanism. So like North Pacific oscillation is the meridional SLP dipole in the North Pacific. So here it is mainly in the winter time it is prominent. So this is mention is as a winter of 0th year. So there is a high pressure in the almost in polar region and the low pressure in the extratropical Pacific. This low actually because of this low pressure there is a westerly wind which reduce the trade wind there, and due to the wind evaporation SST feedback it warm this extratropical North Pacific. But this warming persists though the atmospheric circulation was not there up to summer, and then it influenced the summer North Pacific oscillation, and it generated this kind of wind pattern which actually induce a symmetric westerly over the equator, and this westerly can generate next El Nino event in the subsequent winters. So this North Pacific oscillation can give us a 1 year lead prediction for the ENSO or El Nino event. Now our main focus is this trade wind charging. So this cyclonic circulation in extratropic also give Ekman downwelling, so converge warm water over the extratropic and deepen the thermocline. So you can see there is a thermocline warming here. I try to portray with this animation. So this is like north, south and north part. So you can see this is almost the middle of the Pacific, and we are getting the warming in the extratropical subsurface, which move toward the equators in subsequent summer due to the swag group transport, and then it actually charged the equatorial Pacific with the warm water. and which can propagate again in the eastward and make a East Pacific warming. So I thought I will put very fancy animation, but it didn't work, so it is slide by slide. So based on this study, this is our objective. We try to check this whole mechanism with the ensemble model using the couple model in ensemble approach. So our objective is to isolate the impact of TWC on ENSO variability. We want to improve our understanding how positive trade wind charging. So TWC is a trade wind charging. So positive trade wind charging mechanism is effective to charge the equatorial Pacific and generate the East Pacific warming, and how the coupling plays role when this specific warming is present, and how it evolved in a El Nino condition. And for the first time, we will try to see that how effective this negative TWC to generating a cooling event in the equatorial Pacific. So for this, we have a methodology and model and methodology, which is very crucial for our study because, it is a unique model framework. I will come to that. So we use the CSM and CAR model. This is a ocean and atmospheric couple model. And so this is the initial condition. We run the model and we get the output. So atmospheric model is CAM and ocean model is POP, and it is coupled with the CSM coupler version 7, and C fluxes are calculated using large and eager surface scheme. So this is the couple control run. So we run the model from 500 year of spin-up, which is available online, and with a pre-industrial radiative forcing for 220 years, and we got the output. We will call this output as a CTL, and this long run is actually needed for two reasons, which is very crucial for our run. One is the initial condition for the sensitivity experiment. One is the climatological boundary condition. I will come to that point why these are important. So this is the 220 year of NINO 3.4 SST anomaly for our couple control run. So just recap. So this area is the NINO 3.4. So it is the just like any other central equatorial Pacific. So you can see there is a dark black line. These are the chosen initial condition. As the model is run from the November, we chose the 31 November initial condition. Means we actually wanted the initial condition and boundary condition influence to reduce in our model simulation, just to isolate the TWC mechanism. So we assume that if the neutral initial, if we get a ENSO neutral initial condition, it might reduce the initial condition influence on the model output. So we use two criteria. So this is the November 0 NINO 3.4 SST. We use that it is within the plus minus 0.5. So it will give us, it will ensure us that there is not much ENSO signal in the surface. And then we also see the subsequent winter NINO 3.4 SST, and we use this plus minus 1 criteria that there is no hidden preconditioning which can end up as a ENSO in the next year. So this is that. These 31 are pass our criteria. So this is the evolution of NINO 3.4 SST anomaly and warm water volume anomaly over the tropical Pacific from November to December, and you can see that the black line has the 31 ensemble for the initial condition, and this gray is the total CTL run. So this spread of our selected initial condition are very less. So, and you can see here it is both the surface SST and subsurface warming is clustered around 0, which confirm that this is the best possible neutral state we can get from the CTL run. So this is the unique two-stage model framework. So I am putting it in one slide, but it is actually 1.5 year work. Yeah. So we got that 31 initial condition. Then we run the model, but we run the model in first stage as a control flux. So we calculated the flux offline, and we put that flux in the flux coupler. So ocean can influence the atmosphere, but ocean only get the fluxes from the imposed forcing, and so it we call the thermal and mechanically decoupled. So because we want to isolate the TWC mechanism, so we did the mechanically decoupled to eliminate all other tropical forcing like Bjartny's feedback, recharge, discharge, and westerly wind burst. And we also gave climatological heat flux because we want to eliminate the extratropical flux of flux event like seasonal footprinting mechanism. So for this, we run the model from November 1st with the imposed forcing up to the July end. Then we expected that we will get a recharge or discharge phase of the equatorial Pacific, and then from there we turn on the coupling to see how this recharge equatorial Pacific in presence of coupling evolve, and we expect output as a El Nino or La Nina according to the forcing pattern. So, but yeah, means we are excited about the result, but we get little surprised with that. So this is the TWC anomalous momentum flux, which we imposed on the climatological fluxes from we applied from November to April, which is the main time that this trade wind charging is strongest. And so you can see that this is the climatological and forcing, and we applied a anomalous forcing here. So actually in CSM model, North Pacific oscillation is not very strong. So we use the soda SI run to generate this anomaly. So Valentina did this work. And so it has done like we remove the concurrent ENSO influence, and we correlated it with the next ENSO state. So we get this kind of strong westerlies over the North Pacific, and then we forced the this as a in our sensitivity experiment. So these are the 3 sensitivity experiment we did. The first one we run with a positive TWC forcing. We called it as a plus TWC ensemble. Then we did same type of experiment, but with the opposite forcing. So we just multiplied the anomaly pattern I showed in last slide with the -1, and we got this minus TWC forcing. And we did another experiment which is NoTWC run, where we only forced the model with a climatological fluxes. So we expected this will give us as a baseline neutral state for the equatorial Pacific without any other mechanism acting on it. So this actually we will use for our analysis as a climatology, and we put all the and we calculate all the anomaly and based on this run. So I just so this NoTWC run is will capture the positive, I mean like seasonal cycle. So you can see that the blue line is the CTL climatology, and the red line is the ensemble of NoTWC ensemble mean. So it is closely proximate. It has a close proximity. So we can and also in the warm water volume. So which is showing that subsurface anomaly also are almost near equatorial, near climatological, representing near climatological state. So now, yeah, now I will go for the result. And yeah, so as I said, it is little surprising but exciting too. So this is the plus TWC ensemble run. I will go part by part, and these first few figures are the ensemble mean anomaly. So it will only shows the spatial pattern of the ensemble mean anomaly for plus TWC experiment. So here when we gave the anomaly, I will discuss that first. So this is the surface anomaly pattern. Here it is SST and tau x, and it is curled in the contour, and SSH, which is the proxy of thermocline, is shaded here. And you can see there is some lines which is showing that this region is means above 95% significant. So this wing pattern is actually the imposed wing pattern which we force the model. It has a negative curl here in the subtropics. So it is giving a Ekman downward Ekman pumping and deepening the thermocline in this region. And you can see that with the forcing continues, the thermocline and deepening also increase. So April we stopped the forcing. And you can see there is a cooling in the equatorial Pacific. This is just because of the easterly in our forcing pattern, which is making the equatorial Pacific cooler. And then we will see that the subsurface anomaly, which is the most important. And you can see this is the temperature average over 5 degrees south to 5 degree north. So it is along the equator. So it is longitude. And this is like a latitude from 10 degrees south to 10 degree north on average over this region. So when we started the forcing, there is a building up of a warm water volume or heat content in the subsurface Pacific, and then it mainly in the off equatorial region, then it propagate towards the equator here, and end of the forcing there is a strong charging in the equatorial Pacific, which was our main aim to produce a charged equatorial Pacific. So now I will here show that I showed here that how the subsurface heat content for all the ensemble. This is the warm water volume anomaly for all the 31 run. You can see that consistently this red, which is the plus TWC run ensembles, are able to generate a positive warm state in the subsurface, and the PDF of these two run is distinctly different when we did it with the March, April, May warm water volume. So we able to generate heat, means subsurface heat content consistently for all the ensembles. Now we will allow this charge or subsurface heat content to propagate eastward. So we allow it to propagate eastward with the climatological forcing. So we didn't give any other anomaly forcing. So there is no wind pattern here, you can see, but there is a movement of the equatorial Pacific thermocline toward the east, and where the subtropical one propagate westward due to the Rossby wave response. And by the July there is a warming in the equatorial Pacific because of this eastward propagation of the deeper thermocline warming, and it reach to the shallow thermocline region in east and impact the SST there. And you can see here most warming is around the equator, not the off equatorial region. Now we turn on the coupling to see how this anomaly, which is forced by this TWC run, evolve in the when ocean and atmosphere is coupled each other. So you can see that there is a warming when so September after turning the coupling on, and it induced a westerly wind over the equatorial Pacific. So this set a Japanese feedback. So warming induced the westward wind, and it again means give a positive feedback to the warming, reducing the upwelling. And so this subsurface warming propagating towards the east and having East Pacific warming. Then because of the this Bjerknes feedback, this subsurface warming intensify more, and it give a mature El Nino phase for our TWC positive run. Now how the negative forcing run have evolved. So this is the minus TWC ensemble mean. So for better understanding, I will compare it with the positive run. So you can see that in April, this SST and surface thermocline pattern is entirely opposite of the positive run. So it is giving a discharge phase in equatorial Pacific, but when it evolved with the coupling, it didn't turn up as a La Nina event. It is showing a weak warming. So maybe this August you can see there is a still warming here instead of cooling. Whereas for positive TWC run, whole East Pacific is warming. Here's we didn't get that kind of mirror image of cooling. So maybe this is the reason that ERC coupling didn't turn out to be as a La Nina event. So here I will show the subsurface anomaly. You can see there is a discharge phase in the April as like a mirror image of the TWC, but this propagation is slower and it didn't reach up to the East Pacific fully, still warming, and that's why maybe it didn't turn up as a La Nina event. Okay. Yeah, so now I will show the ensemble, the 31 ensemble. So this plot is looking funny, and Renelis gave him gave this like boomstick plot. So it is a stick and the yeah. So you can see that this is the tropical warm water volume anomalies for the 31 positive run red and 31 negative run blue. And so in the fourth stage it is giving a strong charging in warm water volume for positive and discharge for negative TWC run, and when we turn on the coupling, this signal is still there, that it has a distinct feature of warm and cold subsurface, but this is not as robust as in the surface pattern. So we are not getting the a separation, clear separation. So the the blue one is actually almost symmetrically spread over their mean, whereas the red one has showing the some extreme event. So the red one means like plus TWC run is more effective to generate ENSO El Nino, but not the minus TWC run is not that effective to generate a La Nina. So here again the same plot I showed earlier, but it is with the negative one also. So you can see there is a negative anomaly for the warm water volume, and it is almost in same quantity for the plus TWC run, and these three are distinctly different from each other when we did PDF with the March, April, May warm water volume. But when we did the next year of winter, 3.4 index PDF, the negative TWC run and no TWC run doesn't have any significant difference, but the positive run have shifted toward the more warm event. So it has a more the tail is shifted toward the most extreme El Ninos. So this plot is showing that 31 November next winter SSTs. So you can see there is like warming. It is able to generate the warming, and out of these 31, 18 are the warm event, whereas this, though it is showing some cooling, but it is not very significant because the distribution of the positive and negative event, mainly the significant one, are almost same. So now this is the result end slide. So best, so these are our conclusion. We able to isolate the influence of TWC mechanism on ENSO with our unique model framework, and we found that the plus TWC and minus TWC run is building up positive and negative heat content anomaly over the equatorial Pacific. But the positive run is more positive forcing is more effective for generating the El Nino than the negative run, and 9 out of the 31 cases came as a significant El Nino. But we found that when we turn on the coupling, more than the ocean subsurface, stochastic noise is playing important role for the CSM. And yeah, so we with the plus WDC or minus TWC forcing, we able to provide a fuel to the system, but which we are missing is a proper trigger. So we will try to find that what is lacking in our model configuration. We can do it better or not in our future work. And now I am doing the heat flux experiment, where we are giving the heat flux instead of the tau forcing to the equatorial tropical Pacific. So this is the anomalies we are giving from November to April, and then we are turning on the coupling. So we will see how this evolve as a ENSO or not, and then we are planning to do another run where we will put both the tau forcing and means wind stress forcing and the heat flux forcing, and we'll see which one is more effective to generate the ENSO. Yeah, thank you for your attention.